Welcome to the Deep Dive. Ready to explore some universal laws?
Always.
Today, we're diving deep into Stephen Hawking's A Brief History of Time.
Oh, a
It's a
classic.
journey through centuries of thinking about the universe.
Yeah, from ancient Greece right up to black holes and all that.
Exactly.
Yeah.
It's amazing how much our view of the cosmos has changed over time.
It really is.
You think about those early Greek philosophers figuring out the Earth was round.
Just by looking up, right?
Yeah, like lunar eclipses and the changing position of the pole star. Pretty ingenious.
Aristotle deduced a spherical Earth way back in 340 BC. Talk about ahead of his time.
Seriously. But even with that knowledge, the idea of an Earth-centered universe persisted for ages.
Right, like Ptolemy's model with its 8 spheres for heaven and hell.
That's a whole other deep dive right there.
Yeah. But it shows how science and culture are always intertwined.
Totally. So we're stuck with this Earth-centered view for over 1,000 years.
Until Copernicus comes along in the 16th century and flips the script.
Saying, hey, maybe the sun's at the center and we're just revolving around it?
A total paradigm shift, but not everyone was buying it right away.
Of course not. Big changes take time.
And that's where Galileo and his telescope come in.
Right. Seeing Jupiter's moons orbiting another planet must have been a game changer.
It challenged the whole idea that everything revolved around Earth. Meanwhile, Kepler's refining Copernicus's theory, discovering that planets move in elliptical orbits, not perfect circles.
So many breakthroughs happening all around the same time.
It's like this incredible chain reaction of discovery, and then, boom, Newton publishes his Principia Mathematica in 1687.
That's the big one, right?
Oh, yeah. He lays down the laws of motion and universal gravitation, changes everything.
So the same force that pulls an apple to the ground also governs the planets and stars.
Precisely. It's this incredible unifying force in the universe.
Mind-blowing. But even with Newton's insights, there were still questions about, the stability of the universe.
Yeah, Newton's own laws suggested a universe governed by gravity should either be expanding or contracting.
So a static universe wouldn't really work.
It would be inherently unstable, yeah. Any change in the distribution of matter would cause it to either collapse or fly apart.
Oh, I see. So there was this tension between the idea of a static universe and what Newton's laws were suggesting.
And then you had things like Olbers' paradox, the why is the night sky dark question.
Oh, yeah, that's a good one. If the universe is infinite and filled with stars, shouldn't it be blazing with light all the time?
Exactly. It hinted at a universe that was dynamic and evolving.
So cracks were starting to appear in this static universe model,
Mm.
but it took Hubble's observations to really shake things up.
1929, he observes that light from distant galaxies is redshifted, meaning they're moving away from us.
Wait, so the farther a galaxy is, the faster it's moving away.
That's what the observations show.
It's like the universe is a giant balloon being inflated.
That's a great analogy. Hubble's discovery really revolutionized our understanding of the cosmos.
So we've gone from an Earth-centered universe to a sun-centered system and now to an expanding universe. Each discovery building on the last.
It's an incredible journey of discovery, isn't it?
Absolutely. It makes you wonder what other paradigm shifts might be waiting around the corner.
Who knows what the future holds? But that's what makes exploring the universe so exciting. Before we get to the Big Bang, though, it's worth mentioning that an expanding universe was actually predicted years before Hubble's observations.
Oh, really? By who?
A Russian physicist named Alexander Friedmann.
Friedman.
Yeah, he was working with Einstein's theory of general relativity, and he came up with these models, they're called the Friedmann models, and they describe a universe governed by gravity.
So he was already thinking about a dynamic universe before it was even confirmed.
Exactly. He started with a couple of key assumptions, like the universe looks the same in every direction,
Okay, that makes sense.
and that this holds true from any point in the universe.
So the universe is uniform on a large scale. No matter where you stand on a basketball, the surface always looks the same.
Precisely. And from those assumptions and Einstein's equations, he came up with 3 basic types of models.
Okay.
One where the universe expands for a while and then contracts.
Okay.
One where it just keeps expanding forever.
Yeah.
And one right on the edge where it expands just fast enough to avoid collapsing.
Wow. So many possibilities. Which one do we think our universe is on?
Oh, that's the million-dollar question, isn't it? It all comes down to the rate of expansion and the average density of the universe.
Oh, so it's a tug of war between gravity trying to pull everything back together and the initial outward push of the Big Bang.
Right. If the density is high enough, gravity wins and the universe eventually crunches back together.
And if not,
then it just keeps expanding forever.
Is there enough stuff out there to stop the expansion?
Well, when we add up all the visible matter, like the stars and galaxies, it doesn't seem like enough.
But what about dark matter?
Oh, yes, dark matter. The mysterious stuff that we can't see, but we know it's there because of its gravitational effects.
Right, it's like a cosmic ghost.
Uh-huh, in a way. But even with dark matter, we still don't seem to have enough to cause a recollapse.
So the universe is just going to keep expanding.
It seems likely, but we can't be sure. There could be other forms of matter or energy that we haven't discovered yet.
So the fate of the universe is still a mystery.
For now, yeah.
That's a bit unsettling, but also kind of exciting.
I agree, but even if it is going to collapse, it won't be for billions of years.
So we've got time to figure it out.
Exactly. Now let's shift gears a bit and talk about the Big Bang itself.
Okay, let's do it.
If we rewind the expansion all the way back, we get to this point where everything was incredibly dense and hot. That's what we call the initial singularity.
So the Big Bang wasn't really a bang at all.
More of a rapid expansion from an extremely hot and dense state.
But what caused that expansion in the first place?
That's a question that still puzzles physicists. At that initial singularity, all our current theories break down. It's a point where space and time as we know them cease to exist.
It's almost impossible to wrap your head around.
It is, but it's the prevailing theory based on all the evidence we have.
Were there any other theories to explain the origin of the universe?
Well, there was the steady-state theory for a while.
What was that all about?
It proposed that the universe had always existed and was constantly creating new matter to fill in the gaps as it expanded.
So, no beginning, no end.
That's the idea. But it ran into problems when observations started to contradict its predictions.
Like what?
Well, for example, it predicted that the universe should look the same at all times. But we see clear evidence that the universe has changed over time.
Right. We can look back in time with telescopes and see that galaxies used to be different.
Exactly. The steady-state theory couldn't account for that, so it was eventually abandoned.
So we're back to the Big Bang.
It's the best model we have for now.
And it all started from this infinitely dense point.
That's the current understanding.
It's amazing how far we've come in our understanding of the universe.
It really is a testament to human curiosity.
Well, I'm ready for more. What's next on our cosmic adventure?
Well, next up, we'll explore another fascinating consequence of Einstein's theory of general relativity.
Oh!
Black holes.
Now that's a topic I can get behind. I've always been fascinated by those cosmic enigmas.
And for good reason. They're some of the most extreme objects in the universe.
They challenge our understanding of physics and reality itself.
And as we'll see, they're not just about swallowing things up. They play a key role in the evolution of galaxies, in the fabric of space-time.
I'm already hooked. Let's dive in. All right, black holes, those cosmic vacuum cleaners that suck up anything that gets too close.
Well, not exactly vacuum cleaners, but yeah, their gravity is so strong that not even light can escape.
Right, the ultimate point of no return. But the idea of something so dense that light can't escape, that's been around for a while, hasn't it?
It has, yeah. Back in the 18th century, John Mitchell came up with this concept of dark stars.
So the seeds for the idea of black holes were planted long before Einstein.
Exactly. But it was Einstein's theory of general relativity that gave us the framework to understand how they could actually form.
Right, because his theory showed that gravity isn't just a force, it's a warping of space-time itself.
Exactly. Imagine a bowling ball on a trampoline. It creates a dip, right? Now imagine something infinitely denser and heavier. You get a kind of gravitational sinkhole, a black hole.
So if enough mass is concentrated in a small enough space, boom, black hole. But how do they actually form?
Well, the most common way is through the death of massive stars. When a star runs out of fuel, it can no longer support itself against its own gravity.
So it collapses in on itself.
Exactly. And if it's massive enough, this collapse just keeps going until all its mass is squeezed into an infinitely small point, a singularity.
A singularity, another one of those mind-bending concepts where our current laws of physics break down.
Yeah, we don't really know what happens at a singularity, but we do know it's surrounded by an event horizon. That's the boundary beyond which nothing can escape.
Not even light. So once you cross that line, you're gone forever.
That's the current thinking, yeah. It's like a one-way door in the universe. But here's a twist to the story. In the 1970s, Stephen Hawking made a pretty groundbreaking discovery.
Huh?
He found that black holes aren't entirely black. They actually emit radiation due to quantum effects near the event horizon.
Wait a minute, I thought nothing could escape a black hole. How can they be radiating anything?
It's all thanks to the weirdness of quantum mechanics. At the subatomic level, particles and antiparticles can just pop into existence out of the vacuum of space, only to annihilate each other an instant later.
So empty space isn't really empty at all?
Nope, it's a seething cauldron of quantum activity. Now imagine this happening near the event horizon of a black hole. One of these virtual particles might fall into the black hole while its partner escapes.
And that escaping particle is what we see as Hawking radiation.
Exactly. It carries away some energy from the black hole, making it look like it's radiating. So black holes are actually slowly losing mass over time.
So they're not eternal.
Not technically, no, but the evaporation process is incredibly slow. A typical black hole would take longer than the current age of the universe to completely evaporate.
So we don't have to worry about them disappearing anytime soon.
No, not for those big ones. But there could be smaller black holes out there called primordial black holes.
Primordial.
Yeah, these are hypothetical black holes that might have formed in the super dense conditions of the early universe right after the Big Bang.
So like baby black holes from the dawn of time.
Exactly. And some of them could still be around today, slowly evaporating and emitting Hawking radiation.
If we could detect that radiation, we'd be looking back to the very beginning of the universe.
It would be an incredible find.
Well, this has been quite a journey. From Aristotle to black holes and the Big Bang, it's amazing to think how far our understanding of the universe has come.
And we're still just scratching the surface.
There's always more to learn and discover. That's what makes it so exciting. Thanks for joining us on this deep dive into a brief history of time. Until next time, keep questioning, keep exploring, and keep looking up at the stars.